So limits, this whole unit is on limits, and then after that we do derivatives, antiderivatives, and stuff like that. But this whole unit's on limits. So consider the geometric sequence, which we did in grade 11, half, a quarter, an eighth, a 16th. The sequence can be represented by Tn equals 1/2 to the n, right? We kind of did geometric sequences in 30-1 as well, when we did half-life, doubling, tripling, stuff like that. Okay, so we can also write that as Tn equals 1/2n. The sequence is infinite. It's infinite because it keeps going and going and going and going and going, and unless I ask you up to whatever term, it's going to keep going, correct? The value of each term keeps getting smaller and smaller and smaller as it approaches infinity. So we started off at a half, then a quarter, which is 0.25, then 1/8, then 1/16, then 1/32. It's going to get super, 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 super tiny, right? It's going to keep getting smaller and smaller and smaller. So actually, the value of the term keeps getting closer and closer to 0, because what's going to happen is you're going to get, for example, a half is 0.5, a quarter is 0.25. Then an eighth is 0 point something. Then you're going to get 0.00 something 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 as you keep going. Then it's going to get 0.00000 something 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 when you turn those fractions into decimals. Okay? So as you keep turning them into decimals, you're going to get zeros, decimal, more zeros, and a number, which basically we could round that to 0. Now, does it actually equal 0? No, but it gets closer to 0. So that's what the limit is. A limit, which you have to wrap your head around, is the values that are close to that value as you approach the value. So if I asked you for f of 2, you would tell me what the y value was when x equaled 2, correct? But if I ask you for the limit as x approaches 2, you're going to tell me what the values are on as it gets closer and closer to 2, but not exactly at 2. So how is that any different, someone might say? Well, if I give you piecewise functions, for example, and this was 2 here, I could actually have a value of 2 here, correct? But I could have from the left of 2 and the right of 2 a graph doing this. So as I approach 2 from the left, it would actually be approaching, say, 4, the limit. As I was approaching 2 from the right, it would actually be approaching -4. And f of 2 would actually be 1. They don't have to be the same thing because we're going to use piece graphs, not all continuous. It will make sense. It will make sense. I'm just wrapping your head around it.
So when we say we have like an intersect, right?
Intersect? Intersect? Asymptote? So we can say the limit is 0. The limit 0 is a value that the term approaches but never reaches. It could possibly reach that value at the actual x value, but it might not. The limit is just what it's approaching from the left and from the right. Bear with me. Put down your phone. That might help it. Okay. The limit 0 is a value that the term approaches but never reaches. So this is the notation. This is how it's written. The notation is the limit as n approaches infinity. So as my x value approaches infinity of 1 of 2 of n to the power of n, it equals 0. So what's that saying? As I'm approaching infinite numbers of x, this graph is approaching 0. It's getting closer and closer to 0, which it is, because as I was doing that sequence, it kept getting closer and closer to 0. It would be 0.0000, a number. So it's just the lovely notation. This just means n approaches infinity, or n approaches 6. That's all the little arrow means. Okay? So given f of x equals x squared minus x minus 6, find f of 4. Your heart should be singing right now. You can all do this. F of 4. We did this in grade 10. You can do this. So f of 4. So we fill it in. We go f of 4 equals 4 squared minus 4 minus 6. So it equals 16 minus 4 minus 6. So it equals 6. So remember, whenever you do function notation, that's really just a coordinate, right? The coordinate is at 4 and 6 for that graph. We agree? Now it's actually a continuous graph, x squared minus x minus 6. It's a continuous graph, okay? Now, This is why we went through completing the square. If I want you to graph this graph right now, you'd be like, I'm just going to plug it into my y. No, you're not, because you don't have that calculator. You actually are not going to plug it. You could, but on the test, you can't. So that's a problem. So the only way we'd be able to graph this actually is we need the vertex. How do we get a vertex? 2. So you have to? Yes, okay. So we get f of x equals, we take the 1 out of the first 2, which does nothing. We add a blank. We minus a blank. And we minus 6. To get the blank, we do b divided by 2 squared. Our b is -1. So we're going to do -1 divided by 2 squared, which is a quarter. So we get 1/4. Then we get f of x equals 1 x, and we can look back one, minus a half squared. And technically you have to multiply these, but because it's a 1, it's not going to change it, right? So it's going to be minus a quarter minus 6. In order to put them together, we need a common denominator. So I'm going to have to multiply this by 4/4 because it's 6/1. I'm going to multiply it by 4/4. So I'm going to get f of x equals 1 x minus a half squared. And this be 10 and 1, so minus 11/4. So what's my vertex at? Oh, 25. Good math, Lepp. Good math. 25. That said 25 the whole time. I have no idea what you're talking about. That's a really nice looking 25. So what's your vertex at? Yeah. Right. Because if we did transformations, our normal vertex is at 0, 0, and we moved a half to the right and 25/4 down. Okay? So if we wanted to plot that, we'd have to plot it at 0.5 and then, oh goodness, it would be 6.25. It's 6.25. You can do in your head. Okay. And you have a basic calculator, you'll be just fine. Okay. So you're going to go to a half and negative 6.25. To be something like this. How could we get the rest of our graph because we don't have a graphing calculator? Well, if we're going to look at limits, we're going to need the actual graph. We'll for sure need the graph on both sides of 4 because we're looking at the limit as it approaches 4. Yeah, but we need a more accurate graph. Yes, we need more values. How can we get more values?
You draw a table first.
Yes, a table. We already have one. We already have one. One of them's at 4 and 6, right? How could I get one on the other side? You could do 0 and negative 6. Why? 0 and negative 6. Why? Why is that a point? Anyone? Anyone? Bueller? Yes. It's the y-intercept. If this is in general form, our constant at the back is our y-intercept. Or, hey, we can fill in zeros. 0 squared minus 0 minus 6 is negative 6. So 0 and negative 6. This is going to be a really terrible graph because, well, I didn't draw very good. Oh, this is a half. It's like here. What we need the most for this graph is actually the value at 4. We need to know the value at 4, and we need to know how the graph goes on both sides of 4, what it looks like on both sides of 4, because it's asking me the limit as x approaches 4. So it asked me for f of 4. F of 4 was 6. Then it asked me the limit as x approaches 4. I actually don't care at all about any of the rest of the graph other than the right and left-hand side of 4. So on the left-hand side, as I'm approaching 4, what value am I approaching for the y? 6. The right-hand side, what value am I approaching? 6. So the limit as x approaches 4 of f of x is 6. In this case, the limit and the function at that value are the same. This happens when your function is continuous. So this is a continuous function. It's a quadratic. It's going to be continuous, right? When your function is continuous, your limit will be the same as your value at that function. Does that make sense? So f of 4, the limit as approaches 4 will be the same. Yeah. It will make sense as we go along. Oh, yeah, it's great. Kind of. So limit is just as you're approaching from the right and the left, what do they approach? Okay, if they approach the same value, you can write it. Okay, here the limit is the same as f of 4. However, this will not always be true. The limit is how a function behaves near the point being considered, not the actual function, the value at that point. So in this case, it was the same value, but if like when I drew that other one, it was approaching like this and approaching like this, then it wouldn't be the same, right? Because it's not a continuous graph. So to determine a limit, we must consider a left and right limit. In our example, we consider what happens to the value of the function as x approaches 4 from the left and from the right. From the left and from the right. So we can do this with a table of values to show it working that way as well. So if I pick from the left as I'm approaching 4, I'm going to get closer and closer to 4. Okay? So if I start off at 3.5, I'm kind of close to 4. 3.9, I'm getting closer to 4 from the left. 3.99, I'm getting quite close to 4. 3.999, I'm getting quite close to 4. I could go 3.9999999 forever and see what the value is. How do I get the y value that correlates to those x values? Yeah? Yeah, just plug them into the equation. So you're going to go, the equation is f of x equals x squared minus x minus 6. That's the equation you're going to plug it into. So you're going to go 3.5 squared minus 3.5 minus 6. And a basic calculator can do that. No, you can literally just go 3.5 squared. You'll have a squared button on your calculator. Oh. You just go 3.5 times 3.5. Just use your calculator. Quit. Okay. When you plug it in, you get 2.75. So as we're starting to get closer to 4, our y is at 2.75, but that's at 3.5, right? So I need to get closer. That's still not very close to 4. 3.5 is actually quite a distance from 4. So 3.9, that's getting closer. When I plug that in, I got 5.31. When I take 3.99 and I plug that in, I get 5.9301. What am I getting closer and closer to? 6. When I plug in 3.999, I know this is usually when people start to be like, this is starting to make a sort of a little bit of sense. Then I plug in 3.999 and I get 5.993001. So from the left, I can say it's approaching 6, right? How do they represent from the left? They go the limit as x, this should not be a double arrow. I'm not sure why it's doing that. That's awesome. As x approaches 4 from the left, it should look like this. Just one arrow. From the left, you get a negative exponent on right after, and from the right, you get a positive exponent right after. But when it printed it to Smart Notebook, it did not like what I had, so it did this. That's good. So from the left, it's approaching 6. This one's going to look like this. The limit as x approaches 4 from the right. So it's a positive exponent. So if I do from the right, I need to get closer to it from the right. Okay, from the left, I went 3.999999. From the right, I could do 4.5, something like that if I want to, but that's still quite a ways away. So I started off with 4.01, because that's pretty close to 4. And if it's on the right-hand side, it's bigger than 4. If it's on the left-hand side, it's less than 4, right? Then I picked 4. I just want to pick what I did because I got the answers. 001. So I'm getting closer to 4. Then I went 4.00001. And then I went 4.00001. If I was rounding to the nearest tenth, that would be 4, right? So I'm getting pretty darn close to 4 at this point. So then I plug those values in to the function. So I'm going to go 4.01 squared minus 4.01 minus 6. And you get 6.0701. Then I'm going to plug in 4.001, and I'm going to get 6.007001. And then I plug in 4.0001, and I get 6.00070001. And then I get 6.000007. What can I say that's approaching? 6. Now this is the big deal. You can have a limit approaching from the left, and you can have an answer to a limit approaching from the right, but you might not have an actual answer to the limit approaching that value completely. The only way you get an answer for this, the limit shouldn't have a double arrow, the limit as x approaches 4 of f of x, that's just the ultimate limit. This only exists if from the right and the left the values are the same. So from the left it was 6, from the right it was 6, so the limit as x approaches f of x, the limit as x approaches 4 of f of x is 6. If this was 6 and this was 2, this would be does not exist. There wouldn't actually be a limit for this value. Yeah. Absolutely. So if the positive and negative signs are on the right-hand side of it, then it's right and left. Yeah. So if from the right and from the left it approaches the same thing, then from limit as x approaches 4, it'll be that value. Yeah. Absolutely. So if it's a continuous function, then if it's a continuous function at that point, so sometimes it's not a continuous function. It'll be like this, and then it'll break off. But as long as it's continuous at the point you're trying to find, then your limit will be the same as the actual f function value. That's what we're doing a little bit different.
Okay.
Yeah. But if you had like a function that was continuous like this, and then it broke and went down here somewhere, any value along here, the limit will be the same as the function. So wherever the graph is continuous, if you're trying to find an x value limit, at any place where it's continuous, it'll be the same. Yeah.
So like
Mm-hmm. The limit, it'll be there because the, yeah. Sometimes when the graphs break off from each other, it'll look like this. So you'll have a function, say for this value, this is what f of that value is, let's say. From the left, it's approaching like this. From the right, it's approaching like this. So from the left and the right, they're actually approaching the same value. So the limit at 2 would be 6, let's say. But the value at 2 would actually be 3. So f of 2 would be 3. but the limit as x approaches 2 would actually be 6. So the limit and the function do not actually have to be the same value. It's just the coordinate. When I'm asking you f of 2, I'm asking you what the y value is when x is 2. So it's a broken graph. A lot of the graphs you'll see now are piecewise functions. They're just pieces. Like they're not like an actual nice flowing function like you guys did in 30. Okay, next page. We're going to skip example 1, and we'll come back to it, because if I did it right now, I'd lose half of you. So we will come back to it once the rest makes more sense. Okay? So a limit only exists, this is important, a limit only exists if the left and right limits both exist and are the same. So if the left limit, the limit as x approaches a from the left of f of x, is the same as the limit as x approaches a from the right of f of x, then the limit as x just approaches a of f of x is the same as these two. So like I said, the limit as I approached from the left was 6. The limit as I approached from the right was 6. So the limit as I approach just the value is 6. Okay? So let's look down here. We'll come back to example 2. Don't freak out like you're leaving an example blank. I can't handle this. We'll come back. Okay. Example 2. Explain what it means to say that the limit as x approaches 1 from the left of f of x is 3. What does that mean? Yeah.
So like the left side would be towards it,
Coming towards,
the limit
which is?
3.
Yes. So as we're approaching the value of 3, as we're approaching the value of 1 from the left, my graph is approaching 3. Okay? This one means as I'm approaching my 1 from the right, my graph is approaching 7. The easiest way to explain this is drawing a graph. So I'm going to show you. So we're looking at the value of positive 1 here, right? So we're at 1. Now remember, it's approaching it. So does it have to equal those values at 1? No, it could be open dots, correct? Some people will say, well, how do you know it's exactly like that? The graph doesn't have to be exactly like this. I'm just doing a sketch. You could tweak it a little bit and it would still work. Okay? So from the left, I'm approaching 3. So I'm going to do an open dot at 3. And then I need to somehow get there. So I could go up towards it. I could go straight across to it. I could come down to it. It doesn't matter, as long as when I get to that value, I'm approaching 3 from the left. So I could make a graph that comes down like this. I could make a horizontal line that goes directly to it, or I could come up to it, and all of those graphs would be correct because I haven't gotten any more information on it. If they want it more accurate, they'd have to tell me that on that side it's going to infinity or positive infinity or negative infinity, right? So as long as you are approaching 3 from the left, you're golden. Now from the right, it's going to approach 7. So I could come up to it, I could come down to it, or I could just even completely have a horizontal line coming from it. Pretend that's horizontal, that it doesn't look like it, but it is. So from the left, it's approaching 3. From the right, it's actually approaching 7. It's as you go towards it. People will be like, but your arrow's going this way. That doesn't matter. When I'm coming from the right, I'm approaching 7. When I'm coming to the one from the left, I'm approaching 3. Could I have a completely different value at 1? F of 1 could be 5. I could have a closed dot here. Or f of 1 could be this dot closed. Or f of 1 could be this dot closed, right? They didn't tell me what it is. So I actually have a limit from the left. And I actually have a limit from the right. But do I have a limit when x approaches 1? No, because from the left and the right, they don't approach the same thing. Does this make sense? Is it starting to make sense? This first lesson is always the most painful for me because it's like, just, you'll get it, okay? So if I wrote the limit as x approached 1 of f of x, you would say it does not exist. Because as stated at the very top of this page, if the limit from the left and the limit from the right are not the same, then the limit at that value does not exist. Okay. So we're going to look at some graphs. We're going to wrap our head around what the heck a limit is. That's the hardest part. So we're going to use the given graph of f to state the value of each quantity if it exists, because sometimes it doesn't exist. If it does not exist, we're going to explain why. So this is the limit as x approaches 2 from the left. So take your finger from the left of 2 and follow it up till you get to 2 and see what it approaches. So here's 2. On the left of 2, it's approaching what value of y? 3. From the left, I'm approaching 3. Yeah. Nope. Because all we care about is where it's approaching. The filled in dot matters if they ask me for f of 2. If they ask me for f of 2, my answer would be 3, not 1. Okay. The limit as x approaches 2 from the right. I'm following it from the right. I'm following it. And I'm reaching what? 1. So from the left of 2, I reach 3. From the right of 2, I reach 1. So the limit as I approach 2 is what? It does not exist. And how would I explain that? Well, I'd say because, I want a smaller, the limit as x approaches 2 from the left of f of x does not equal the limit as x approaches 2 from the right of f of x. That's how you'd explain it. Yeah. Now, in some ways, your teacher, because a lot of the questions are written, would ask why, and you'd have to explain why. Right. Yeah. Now, f of 2 does not equal 1 because it's not closed dot. F of 2 equals 3. Now, so whenever there's a break in a graph at the limit you're trying to find, that limit's not going to exist, right? So at 2, I have a break in the graph from the left and from the right, so I know the limit's not going to exist because they're not approaching the same thing. Yeah. Then f of 2 wouldn't exist. Yeah. He asked if this was an open dot and this was an open dot, would f of 2 not exist? Yeah, it wouldn't. It would be open dots, right? There'd be no value for y at 2, which is like 4. Okay. So we're going to look at the limit as x approaches 4. So in order to find the limit as x approaches 4, I indirectly have to find the limit from the left and the right and see if they're the same, right? So not always am I going to say, what's it from the left? What's it from the right? Then what's it at the... If I ask you for this value, I am asking you to look from the left and the right and see if it approaches the same thing. Okay? So from the left of 4, I'm approaching 4. From the right of 4, I'm approaching 4. So if they're the same, then the limit as x approaches 4 of f of x is 4. Now put your hand up if you can tell me what f of 4 is. Yeah, it does not exist. Because why? Because why? Why does it not exist? Right. So there's no y value that correlates with the x value. All right. Try example 4. Note to self, it continues on the next page. So it's A, B, C, and more. Okay? I'm going to try this one out. So, as the limit as x approaches -3 from the left, so I go to -3. From the left, I'm approaching 1, 2, 3, 4. From the right, I'm approaching 4. So the limit at -3 is 4, because from the left and the right, it's the same. Then here I have h of negative 3. What was h of negative 3? It doesn't exist because there's an open dot. Now, as x approaches 0 from the left and as x approaches 0 from the right, let's look at that. So if I approach 0 from the left, I take my finger onto the graph and I follow it down until I approach 0 from the left. What am I approaching? 1. If I take my finger and I approach 0 from the right, what am I approaching? Negative 1. So from the left it's 1, from the right it's negative 1. So if from the left it's 1 and from the right it's negative 1 and there's a break in the graph between those two, what's the limit as x approaches 0? Does not exist. What's h of 0? Which one of these is a filled in dot? 1. Then I have the limit as x approaches 2 and h of 2. So it's just the limit as x approaches 2. So I still need to look from the left and the right even though it didn't specify that, right? So from the left, I'm approaching 2. From the right, I'm approaching 2. So what's the limit as x approaches 2? 2. What is the value of h of 2? Does not exist. Open circle. Now, at 5 from the right, 5 from the left, you might have a different answer than me, but it's just because it's really small and you might not have spotted it. But this actually comes all the way down to here. Oh, down to here. The whole graph comes down to there. It's a really tiny graph. So from the left, it's approaching 2, and from the right, it's approaching 2. You might have put 3, and if you did that, it's just because you saw it approaching 3. It's not, you were wrong, okay? So it's 2. So the limit as x approached 5 in general would be 2. Okay? Now this is where these asymptotes come in, like you were asking earlier. So the limit as x approaches 2 of r of x, this is the function r. So if as I'm approaching 2, from the left, what's it approaching? Negative infinity. As I'm approaching 2 from the right, what's it approaching? Negative infinity. So what can I say it's approaching it to? Does it exist at 2? Is there an f of 2? No, because there's an asymptote. Look at 5. As I approach from the left of 5, I'm approaching positive infinity. From the right of 5, whoa, this is some really bad drawing. I'm approaching positive infinity. So the limit at 5, positive infinity. Now I have 3 from the left. 3 from the left, what am I approaching? Negative infinity. 3 from the right, what am I approaching? So from the right, positive infinity. Is there a limit at 3? No, they approach different things. And what's the, yep. Sorry? Oh, this is supposed to be negative, not positive. That's why. This is supposed to be negative 3. These are supposed to be little negatives. In front of here, it's supposed to be the limit as x approaches negative 3. Sorry. If we did positive 3, though, what would it be? If it approached positive 3. Some weird decimal, that's what it'd be. Negative 0.5. So if this was actually this way, you can leave it this way if you want. That's fine. You can leave it as positives. It's going to be negative 0.5, negative 0.5. So at 3, it would be negative 0.5. You can do it either way. You can leave it as the negatives and make it the infinities, or you can leave it how it is and make it be the 0.5. The asymptotes are at x equals, not y equals, because whenever you get a vertical line, it's x equals, right? Negative 3, 2, and 5. Negative. It's just the y value at 3. If I follow the y value down at 3, it's negative 0.5. That's all. If you did negative 0.4, I couldn't really ding you on it, kind of thing. So the homework is short. It's not the whole thing because I only did a part of the lesson. In this textbook, there's only answers to the odds. So we often go through the evens first in class, so you can actually do the odds. But the reason why they do that is the teachers often will use the evens for assignments and stuff like that, because then you won't have the answers to them. What's great about this is there's this thing called Slater, this website called Slater. Slater is a website, I think that it made up by university students, but I'm not sure. Page 96, numbers 1 to 9, odd.